Hi, my name is Qisong. Today, I'm gonna tell you a bit about our paper, Training and Transferring Safe Policies in Reinforced Learning. This is joint work with Tiago Simo, Niels Jensen, Simon Tinderman, and Matthias Span. I have equal contribution with Tiago. That's it. Let's get started. Reinforced learning has been collecting lots of achievements. Imagine playing chess or some computer games. We usually formulate a RL problem to be a MDP, but the agent has no knowledge about the model, so it must learn from experience. In traditional RL, we can collect experience without safety concerns, but that is not allowed in safety critical problems. To give you an example of how we're gonna formulate the safety, I will use this electric taxi example. In this example, we have a taxi interacting with the environment. This taxi needs to pick up a passenger at some point and drop it in a destination. For electric vehicle, we also have a battery. If we keep it exploring randomly, we may end up running out of the battery. So how can we finish the task without any running out of the battery? But the question is, what is the red penalty for this dangerous situation? It is not easy to use a single reward to specify the desired behavior. So we decouple safety from reward by explicitly using a cost to express unsafe interactions. In this case, we formulate the RL problem to be a constrained MDP, so we can maximize the long-term reward such that the safety cost is below a cost limit. We can choose to use a Lagrangian version of soft actor critic to solve the problem. With a Lagrangian multiplier, we can find a trade-off between reward and safety automatically. And SAC Lagrangian also allow us to use some policy samples to ensure a safe training process. In most cases, safety and reward are conflicting. So it is not easy to find a good balance. Let's see example first. In this car button example, we can see it is quite hard for the car to avoid obstacles and touch the right button. So for a complex reinforced learning problem, if the agent chose to learn from scratch without enough exploration, learning to solve the task safely is quite challenging. And it is easy to get stuck in a suboptimal solution. It is normal to first train an agent in a controllable environment where the unsafe interactions are allowed, then use a learned policy to guide the training in real world, where the unsafe interactions are not allowed anymore. Also inspired by curriculum learning, we consider a setting where we first train an agent without reward signals, but still provide safety signals. So we can transfer the Safe Explorer to better guide the training after the task is revealed. We also propose safe transfer metrics. When we do the unsafe transfer compared to start from scratch, we use safety jump start to indicate how much we can improve to be much closer to a safety limit at the very beginning of the training. We use a dirt time to safety to indicate the difference in the number of interactions required to reach the safety threshold. We may do a safe transfer. A training agent might start with expected cost of return lower than the safety threshold. In this case, safety jump start would be the difference between the safety threshold and the cost of return of an agent learning from scratch. Similarly, their time to safety would be the number of interactions the agent learning from scratch needs to satisfy the safety constraints. Once we develop agents that learn without violating the safety constraints, we can also consider the social metrics of transfer learning with respect to the real world. For instance, an initial improvement in terms of performance, which we call return jumpstart, and the time necessary to reach optimum performance, we call this the time to the optimum. For our transfer learning setting, we consider a single source task that only provides safety signals, which we use to train the guide. Without a reward signal, the guide aims to explore the world safely and efficiently. We are interested in using this guide's safe exploration ability to help the training student on the target task without violating the safety constraints. In the source task, we first consider to maximize the policy entropy under the safety constraints, but also max policy entropy tends to have diverse behaviors that does not imply efficient exploration of the environment. So to enhance exploration of the guide, we adopt a auxiliary reward that motivates the agent to visit novel states. Now, we finished to train a guide in a source task. Then the question is how we can use it to help the training of a student in the target task. Firstly, we can consider how to use a guide agent to make the student quickly learn to act safely. With a mapping function sheet to map the observations between tasks, the transferred policy can be used to regularize student policy towards guide policy using KL divergence. But as a student becomes safe, we should try to eliminate the influence from this KL divergence term. But that is not enough to ensure the safety during training. So we use a composite sampling strategy. The safe guide policy will help to ensure the safe interactions with the environment. That means our behavior policy is a mixture of the guide policy and the student policy. We investigate two strategies to define the behavior policy. The first strategy is linear decay. We decrease the probability of using guide with a constant decay after each iterations of the algorithm. So we gradually increase the probability of using the student policy to sample. Our second strategy is control switch. We use control switch to generate more on-policy samples at the beginning. This strategy starts each episode sampling from the student. When we met first positive cost, it switched to the guide policy and follow it until the end of the trajectory. To verify our method, we first do exploration analysis. Compared to only maximize policy entropy, our auxiliary reward distance bonus can get more efficient exploration. Then we can have a better guide for training in the target task. That means we can also from this difference to check whether a better guide will result in better students. With this safe guide, we can basically ensure the safe interactions with the environment. It's quite a big improvement compared to learning from scratch and pre-train the agent in the reward-free task. Let's see the videos. From the videos, we show the final performance of the learned policies. We can see compared to learning from scratch and pre-training in the reward-free task. Our safe guide can really help the student to achieve a very good performance, both in reward and safety. To conclude, the constrained reinforced learning is a very interesting framework to study safe reinforced learning because this allow us to explicitly model the safety requirements. We do not need expert anymore to figure out what is a good balance between safety and reward. Second, the algorithm we propose can ensure the safety during training in the target task. And guided by a safe explorer, we can make the exploration in the target task more effective. That's all. Thanks for listening. And I'm very happy to be here. If this research interests you, please come by our paper. Thank you.